All right, so we're taking out our intro worksheets, and I do want to make sure we understand these calculations that happened on the last 2 pages. And I had you skip the acid-base indicators. I'm going to talk about that, and I'm going to talk about table L as well. Okay, so drop something. So first and foremost, we know that water, H2O, undergoes something called auto-ionization by itself. This is weird. Very weird that water does this because it's a molecular compound. Normally molecular compounds don't do this. The exception are acids, where you slough off ions. Normally only ionic compounds make ions. So acids are the exception to covalent compounds that make ions, but they only make ions by H's coming off, okay? Any case, water becomes H plus and OH minus. And this is a liquid, aqueous. This is aqueous. All right. Now, it is not a completion reaction. It does not completely go forward. It goes in equilibrium. Okay. Let's write an equilibrium expression because we do so because we want to see how far the reaction goes forward. So what we do is we do products over reactants, coefficients become exponents. So we put brackets around and say it's the product of all the products here. So products over reactants, but the reactant's a liquid. Products over reactants, coefficients become exponents. Solids and liquids do not apply. So that should go on the bottom, the denominator. But because it's a liquid, it's over 1, and that's why I read it this way. And this equals KQ. But that KQ is special for water, so we call it KW. And we have measured that value. That value we have measured to be 10 to the negative 14, or 1 times 10 to the negative 14 if that makes you happy. And what does that equal? Well, if you've got pure water, no acid and base, and every one of these makes one of these and one of these, then you need to understand that the molarity in between brackets represent molarity. That molarity has to be the same number. Well, of course, it's 1 times 10 to the negative 7. 1 times 10 to the negative 7. Party people, those are tiny numbers. Tiny numbers. Okay? But they're important numbers because knowing what the concentration of the H plus or the hydroxide is so gosh darn important to us. Why? Because life can only exist between a narrow range of those concentrations that in water are naturally very small. Why? Because hydroxides will break bonds by pushing their electrons. H pluses will break bonds by grabbing electrons. So only when they're in very, very tiny concentrations, okay, are they safe. Okay, so it's important to realize that. So water barely goes forward. Look at its KW. What have we learned? If a Ka is big, greater than 1, what does it mean? There are more products than what? Right, and if KQs are smaller, who's favored? More reactants. This thing is tiny. There's 13 zeros in front. This thing barely goes forward. Okay, but it does. And these values are very low in water. That's why water is safe. Water has H pluses in it. It has hydroxides. It could be corrosive or caustic, but at such low quantities, it's safe for us. It's only when one of these two get higher. That's really important. You see why we look at it. So what is pH? Well, pH, and it's important you understand, pH is the negative log. The little p means negative log of the what? H plus concentration. Now, I need to write in also H3O plus. H3O plus is synonymous. Okay? And so, why do we do this? Why do we use a scale where we're using this? Now, what's negative log mean? If you haven't learned about logs, it's a great way to learn about logs. We're using a base 10 logarithmic scale. And it's a nice little scale because 10 to 1, 10 to a 2. This, of course, is 10 to the 1. This is 10 to the 2. This is 10 to the negative 1. This is 10 to the negative 2. All I'm describing is how many zeros in between a number greater than 1 or less than 1. 10 to the negative 3. 1, 2, 3. So the movement of the decimal place in a direction that makes the number smaller or bigger. So it's a nice little scale. And why do we use it for pH? It's a convention. Because the range of possibilities for these values is huge, huge. We can go from 10 to 0.0000000000000001 about. That's the range of possibilities for every one of these ions. It is cumbersome. So what is the value of the H plus ion concentration? Mr. Grodsky, it is 0.00. No one wants to deal with that. Even people don't want to deal with this. 1 times 10 to the negative 7 or 8. They don't want to deal with that number. So what they've done is take the entire number, and it won't always be 1 in front, and stuff it into an exponent. So the pH is nothing more than an exponent that represents the entire number. This one's easy because it's 1 times 10 to the negative 7. Oh, and people don't like negatives, so what do? We times it by a negative 1. So when I say log of something, take that number and put it into the exponent base 10. It's easy. You can do it by hand if it's 1 times 10. If it's 2.2 times 10 to the negative 7, you need your calculator. Okay? Now, don't forget, there's an alter ego here. This is also can be negative logged. And that would be your POH. And of course, the POH is equal to 7 as well. And we learned that a neutral pH with no acid and base has a pH of 7 because these are equal. Okay? So understand, the pH scale. There's also a POH scale. No one uses that, but know it exists. Don't confuse it. So when I have a pH of 7, what are they talking about? Well, a pH of 7, okay, means that my H plus ion concentration, or H3O plus, is really this. 1, 2, 3, 4, 5, 6, and a 1. Or 1 times 10 to the negative 7. They think that this is cumbersome because it's a huge range, so they stuff the entire number into an exponent. Okay, that's the reasoning. All right, now, party people, some basics that we went over Friday, just covering. Okay, what do we know? Well, because these are exponents, 7, which is the pH, it's the exponent here, and the POH is also a 7, has to equal a 14. Now what's 14? Negative log of this number is 14. And by the way, that's the little pKw. Okay, so that's what that is. And what do you know when you multiply what? Numbers with exponents, you add the exponents. pH scale or exponents. Now it's important you realize they're base 10 exponents. What I mean by that is, if I've got a pH of 5, starting easy, and I go down to a pH of 3, people will say, hey, the pH dropped 2. Wrong! I went down 100 times. The pH went down 2 exponents base 10. Right? Didn't it go down? So we would say, what would be the H plus ion concentration if the pH was 5? This would be 1 times 10 to the negative 5, keeping it simple. By the way, 5 plus what is 14?
9.
POH should be 9. pH is 5. POH is 9. Okay, notice what happened. By me going from a 7 to a 9, I increased the acidity. I just added an acid. And my pH went from a 7 to a 5. I went from a what? 10 to the negative 7 to 10 to the negative 5. This number got bigger or smaller? Got bigger by how much? By 100 times, by 10 to the 2. So we would say the acidity increased 100 times. The reason why the pH drops is that as this number gets bigger, its negative exponent gets smaller. Now, pH of 5 is not dangerous. This number is getting bigger. What if this becomes a pH of 1? Hey, 10 to the negative 1. pH is 1. This becomes a what? 13. Negative 13. Hey, that is what? 0.1 molarity. That can become corrosive to our bodies. Okay? That's getting dangerous. So it's important you realize that. Now, how do we go backwards? How do I go from the pH or the POH back to the actual value? Since this is an exponent, and we did negative of the exponent, we go 10 to the negative x backwards. What's 10 to the negative 1? Negative 1. To go backwards here, I'd go what? 10 to the negative 13. Why do I go negative? Because we times it by negative. Sometimes they call that the anti-log. And on your calculator, they have the log button. And I think the second function is the what? 10 to the negative x. Or it's the other way around. I'm not sure, but they're on the same button because they're equal and opposite of each other, if you want to think of it that way. Okay? So that's important that you understand that. All right? But let's continue on. So you had some problems this weekend. Hopefully you didn't have a lot of problems with this. But now that you have those basics down, sorry for the pun, all right? And I think I wanted this table here. Okay, so let's look at this problem here. What is the pH of NHNO3? Well, if you go to table L, and you're going to have table L for your test, okay, it's a strong acid. Strong acid. What does that tell me? Its Ka is what? Through the roof. It's approximating infinity because it completely dissociates, which means the molarity, which is moles over liter, of my acid is exactly the molarity of my protons. Every one of these breaks apart into a free H+. You can assume that if it's a strong acid. So this is the concentration of my H+. Notice what I wrote here. The concentration of the acid is the concentration of the H+. Great. How do we get pH? Once you have the concentration, you negative log it. Now you can't make the pH what? 3 here. If it was 1 times 10 negative 3, I could. So I got to do, I type in my calculator, negative log, put this number in, and it gives me my pH at 2.5, which I expect to be low. So if you haven't done that yet, okay, I go 3.4, second function EE. I like to do the EE key because I don't like carry key, all right, because I want to tie it together. Negative 3. So I have 3.14 times 10 negative 3, or I can do this. Negative, hit the log key, 3.4, second function EE to negative 3, close my parentheses, and that's what I get. Woo! Up close and personal. And what do I get? It's too up close and personal. So what I get, maybe, and all I did, party people, negative log, and I get 2.46. 2.5 I'm going to round to. Everyone get that? That's it. Very simple. Okay? So let's go on to another one. Now, this one's a little trickier. Okay? So now, you've identified what this is. Barium hydroxide. Based on solubility rules, barium's a group 2 what? Ion with a hydroxide. This is a strong base. Now, it's a salt that has hydroxide in it. It's soluble. So when it dissolves, there's going to be twice as many what? Hydroxides. So this is the molarity of barium hydroxide. But there are 2 hydroxides for every one of these. So that's why I times it by 2. For every one hydroxide, every one barium hydroxide, there's 2 hydroxides. So I'm multiplying this by 2. That's my stoichiometry. I can lay it out for you and cancel out the units, but you should be able to see that. Hey, strong base, all the hydroxides. This is the moles per liter of this. Hey, they're twice the moles in the same volume. The molarity doubles. And now I'm stuck with this. Now, big mistake people make. They do negative log and think they're getting the what? pH. Ah, you're getting the what? Negative log of the hydroxide is the POH. So, don't make the POH 4. It's not 1 times 10 negative 4. It's that big number. You're going to have to put negative log 4.96 times 10 negative 4, okay, and find that number. And I find the POH. Now, what do we know? For me, it's easy. Once you have the POH, subtract from 14, you got your pH. Okay? And that's what I did here. Because I know what? Okay? The pH plus the POH equals 14. And I get 10.7. Not hard. Not hard. Okay? Right? So that's really what those questions were about. All right? All right, so those are the kind of questions that you should be okay with. All right, so let's move on to table L. All right, and again, the rest of these questions are very similar. Okay, if you look at the bottom one here, how many moles of HCl needed to neutralize? Now, the word neutralize means you're going to match an H plus up with a hydroxide, right? So you have calcium hydroxide. It's a base. It produces hydroxide. Hydroxides are potentially dangerous. You can add H pluses to match up with them. So how many moles of HCl needed? Well, the question is, how many moles of hydroxides are given? Okay, what did I give you? I gave you a POH, I gave you a pH of 10.6. So what do I do with that? I gave you a pH. Here, think about the problem. We want to find the moles of another acid needed to match up and react with all the hydroxides. Don't forget, party people, neutralization is going this way. Does this go forward really well? Does this break apart really well? Here's the equilibrium constant of this reaction. Terrible. 1 times 10 negative 14 is tiny. It barely goes forward. That's why water does not conduct electricity. The ions are too small if this is -7, -7. There's just not enough of them. And pure water doesn't hurt us because the amount of hydroxides and H pluses are so low in quantity. Important you understand that. So if this is terrible, going this way must be really what? Incredibly favored to go this way. So if you've got a hydroxide hanging out in solution and you add protons, you can bet your donkey you're going to make water as a completion reaction. Because can you guess what the K EQ of the reverse reaction is? The inverse of that, isn't it? Just flip it. You're right. So that's your stoichiometry in acid-base chemistry. So what I'm saying to you is, how many moles of this do we need to do what? Neutralize. We're going to match H plus with OH minus. That's what neutralize means. That's what we're going to be doing in all our labs. So they gave me a pH of a basic solution. I subtract it from 14 to get my what? POH. Now, that gives me 10 to the that gives me my POH. Hold on. So my POH is 3.14. How do I go from my POH to the actual value of my hydroxide? 10 to the negative 3.14. So I got my POH, and I go 10 to the negative x. That gives me my concentration of my hydroxide. Guess what? How much HCl do I need? The same amount. The same amount. Because I'm matching what? One of these with one of these. Okay. Okay, let's go on to table L. Don't want to take one, but we will. All right, this is important. You'll be given this. You don't have to memorize your top 5 or your strong acids. There's stronger acids than this, but I mean, there are other strong acids. Sometimes there's 7 or 8. People will talk about it on these chemistry forums. It's a good time. But the point is, these are definitely ones you'll see. Now, these are your strong acids. Why? Look where the Kas are. They're so big they don't even write them, which tells me it's a completion reaction. It goes forward. you can assume if you've got a strong acid, every single one of these H's completely dissociates. When it comes to the HSO4, sulfuric acid, H2SO4, we talk about the first H. We'll talk more about that. So what does that mean? This is important. This is important. I know I did this at a home video, but I want to do this live. Think with me what we've done so far. If we're really good at going forward, and the Ka, which is a KQ that's for acid dissociation constant, is really good at going forward, then can it be good at going in reverse? No, you can't do both in the universe. You can either be really good going forward, which means you're going to be terrible in the reverse. There's preferred pathways. So these guys are really good going forward, which means that these are lies, people. Lies. They're not bases. They have no ability to accept a proton back. That makes sense? If these guys could accept a proton back, wouldn't they reform the acid? And if they reform the acid, it wouldn't completely dissociate. So these guys have no ability to do what? Go in the reverse and accept a proton. So we say they're conjugate bases just to be formal, but they have no ability to grab an H from water or anything else. And that's why they're strong. Hey, we talked about it. I's a big -1. It has no what? These guys are big -1 ions. The charges are too low and the ions are too big. Hey, nitrates. Those are 4 atoms stretching out a -1. Coulombically, they can't attract it. All right? So it's important. But what happens when we make a leap here? You go from complete dissociation to barely dissociate. The rest of these are weak acids. Now, what's happening? Their ability to go forward is doing what? Getting worse, getting weaker, which means their ability to go in the reverse is getting right. So what's happening to the strength of the conjugate base? It's increasing. As the acid gets weaker, this is gaining a bigger ability to grab back the proton and reform the acid. That's why they're weak. They're weak because they have conjugate bases that are strong enough to reform the acid. So weaker acid, stronger conjugate base. And party people, if you keep going down, you see any bases that look familiar? Hydroxide ions? Oh, anyone see the acid dissociation constant for water? Oh, that looks familiar. That's KW right there. Did I get it? No. Darn it. Okay, I felt it. Right there. Okay, important. All right. Cool beans if beans are chill. But, party people, there are some issues here. What the freak is that? What is that? I want to teach that to you now. That is called complex ion. Okay, so let's talk about this. Okay, complex ion. Let's talk about aluminum. I got, let's say, aluminum nitrate. I drop it in water, it becomes aluminum +3, and we have the nitrate ions. We all know the nitrate ions do not ionize, do not pull back water. They're spectators for the most part. And I have aluminum +3. Now, how did aluminum eventually become +3? Did aluminum atoms somewhere, what would happen for it to become +3? When I'm an atom neutral, it lost, it got oxidized. So it lost 3 electrons. And we already dealt with the fact that aluminum is pretty darn reactive. We talked about that. You guys picked aluminum as the electrode in lab 2. How dare I interconnect all of this? Now, what happens to the size, the radius of the ion? Here's the atom. It's a big element because it's metals. Look at there. Metals are big. But when you lose an electron, don't think protons outnumber the electrons? So when you lose an electron, what happens to your size? You get smaller. If you lose 3, what do you think you get? Even smaller. So this thing, my friend, is, or my friends, or my enemies if you hate this, it got really small. And if you're really small and +3, what do you think the Coulombic attractions are for the things around it? Higher or large? Incredibly high. How do you know? Coulomb's law. the force of attraction equals Q1, Q2 over R squared. If the charges are high, that's going to make the force of attraction high. And if the radius is small, that means things can feel it. This is going to be hugely attractive. The charge density is incredible. So when that is floating around water, this is what happens. Stay with me. So when this is in water, yes, the negative end of water is attracted, but more than that, it gets pulled so close. It gets pulled, and it gets pulled in so close that only 6 water molecules can fit around it. And we call this thing a complex. Normally the ions, the water surrounds it, but it doesn't stick around it so strongly. Okay? And I'm going to run out of space here, I think. Okay, but you get the idea. So I got 6 waters completely surrounding it. Okay? Now I'm going to zoom this up a little bigger so you can see what I'm talking about. Now there's something else that occurs here. So let me just make this a little bigger so you can see it. Those that, my fans at home, talking about the actual mechanical fans. Here I have the water. And I'll just draw 2 here. And we have the 2 lone pairs here. We have the bonds in between with pairs of electrons. These are molecular substance. Okay, now, what happens is, I know there's 4 more. Because this is so -3, these pairs of electrons are also attracted to the +3. So they actually drift toward the +3. I'll zoom it up even bigger. Here's the +3. Here is the O. Here is the H. This pair is getting what? Pulled even closer to that very highly charged +3 that's very small. And if you keep pulling electrons even more, what do you think the H is going to do? It has the ability to do what? Slough off and become a what? H+. So, here's what happens, party people. We write this complex this way. It looks kind of messed up, but we have aluminum +3. We know it's so highly charged that 6 water molecules surround it. And because aluminum is still +3, and because water is neutral, we write +3. That is called a complex ion. And how do I know? It has a really high charge. +2, +3. Now, check it out, party people. When it gives off an H, hey, this H leaves, right? This is now a hydroxide. How do I write it? Aluminum, H2O. Now there's 5 H2Os, because one of the H2Os became a what? A hydroxide. Now because a hydroxide's a -1, and this is a +3, what's the charge now? +2. And if I keep going one more time, I give off another H. It's harder to do, but it can happen. H2O 4, and now I have 2 hydroxides. Each hydroxide's -1, so what's the charge here? +1. And that is how we can produce an acidic environment by dropping something that has a what? Large charge. The more electrons that are lost, the smaller they are. So, given this, what's the conjugate base of this? Ooh. That means that this is the acid. Do bases have 1 less or 1 more H? Well, bases are good at accepting H's. So conjugate bases always have 1 less. So the conjugate base of this is that. What's the conjugate acid of this? That means that this is the base. It has 1 more H. Remember that? Think of it this way. What's the conjugate base of, even though it's a lie, of HCl? What's left over after it acts as an acid? Cl negative. Right? Okay, what's the conjugate acid of this? HCl. Okay, so it's the same thing. Hey, what's the conjugate acid of HCO3 negative? Well, the conjugate acid's going to have one more, H2CO3. What's the conjugate acid of this? Has one more. What's the conjugate base of this? One less. Same idea. Okay? So if we take this, you had a worksheet that went with this for homework. I'm going to open that up. Pretty simple worksheet. Now, check this out. Aluminum plus 3. What do we really have? We know it's such a positive 3, 6 water molecules. This pair of electrons gets attracted, this comes off. Okay, look at its Ka. 1.1 times 10 to the 5. It's a weak acid, but it's an acid nonetheless. Look at the size, 210. Let's compare that to another ion below. Check this ion out. Fe plus 3. What is the size? This is picometers. This is the size of the ion, 69 picometers. Compare that with aluminum, 210. Whose radius is smaller? Right, if you've got a smaller radius, what does that do to the Coulombic attractions? Yes, the denominator gets smaller, the force of attractions. Who cares? You get smaller, you're stuffing the plus 3 in a small space. Don't you think the what? The electrons are going to be even more attracted to something that's even smaller that's plus 3? So what do you think the Ka is, comparatively speaking? Check that Ka compared to this Ka. Who is a bigger Ka? Yes, why? Because, yeah, exactly. It has a higher charge density. It's plus 3, but even smaller. Check this out. Look at copper. But copper is what? Plus 2. Now hold on. 71 picometers is pretty what? Small. But wait a minute. That's nowhere near. That's much less acidic than what? Yeah, why? 10 to the negative 4. This is 10 to the negative 7. This is 1,000 times, approximately, 1,000 times less acidic. Why? Still pretty small, but what? It's not plus 3. So it doesn't have the same charge density. All of these guys are acids, okay, because they do what? They make these complexes. Okay, last little piece, okay? Christmas in July. Let's go back to, not that, last page. Let's finish this out. Okay, we have something called acid-base indicators. Okay, acid-base indicators. And what these are actually, we're going to talk about these in big deal here, but these guys are actually acid bases themselves. Let me explain. They are chemicals that have a color as a conjugate acid and as a conjugate base. In fact, their colors are different. For instance, look at bromothiamyl blue. Bromothiamyl blue. Now, when it is in its acid form, it has a certain three-dimensional size, it has a certain structure to it that it can actually absorb the yellow part of the spectrum. Okay, which means you see, an acidic condition, okay, and it's telling you this right here. At 6.0 or lower. So anything 6.0 and lower, bromothiamyl blue is yellow. I want you to understand what this means. Its conjugate acid form is such a three-dimensional shape that it can absorb the blue part of the spectrum and you see yellow. When the pH rises enough to be 7.6 or higher, then you have mostly the conjugate base form. Its conjugate base form, when it accepts protons, changes itself in such a way that it can absorb the yellow part of the spectrum and you see blue. When it's in the acidic form and it protonates it, it changes in a way that It can accept the blue part of the spectrum and you see yellow. So these are chromophores. These are chemicals that give color. And we're going to talk about this, but you should understand, if something is giving you color, it's because that this chemical, okay, this chemical, the sugar part of the dominoes here, is absorbing, in this case, the blue part of the spectrum. Right? There are chemicals here. This is white light. The top part here, you see white because they're what? Being reflected. They're not being absorbed. These chemicals here, they have a certain three-dimensional shape to them that they can absorb part of the wavelengths of light. You guys should know this already, but I'm going to make sure we understand it. Okay? And we're going to learn in detail, so hold on to your ponies about that. Remember Roy G. Biv? Red, orange, yellow, indigo. Red, orange, yellow, green. Roy G. Blue, indigo, violet. Now, if you remember this, we learned that, hey, most plants are green. I had a shot. Most plants are green, even though this is orange. Why? Because plants have a photosystem that has a bunch of pigments that can absorb part of the red spectrum and part of the blue spectrum, and you see what's not being absorbed. That's why plants are mostly green. Okay? So the chlorophyll has a certain three-dimensional shape. Well, again, these all have certain three-dimensional shapes. But how do you read this? Very simply. Anything, the first number and lower is what its color is in that range. So you had some homework. I didn't ask you to do it, but now it's easy. For instance, what would be the color of the solution if brome cresol green was added? Well, if the pH is 3.42, and you look up brome cresol green, everything 3.8 is yellow, so this would be yellow. It's just that simple. Okay? I'm not going to hold your hand with that. You have that chart. Let's look at bromothymol blue. That's phenolphthalein we'll talk about, but let's look about bromothymol blue. Okay? Based on the table it gives you, here's your pH change. 6, it's yellow. Below, 6 and below, it's yellow. 7.6 and greater. Now, what's really interesting, I find, is that here is, I know it's kind of weird to look at this, but this is the three-dimensional arrangement, right? So when we draw it like this, here are those circles. So these are carbon-based molecules. But just to show you the complexity of these molecules, okay, here is bromothymol blue. Here is its form in the acidic form. Hey, look, it's holding on to these H's because there's what? Acids are giving off H's, and it changes its structure so that it can absorb the blue and give you yellow. In a basic solution where it's blue, what do bases do? They grab the H's away. And when these are O negatives or O's here, it changes its structure so that it can absorb the what? Yellow part of the spectrum to give you blue. So, to end up with this nice little demonstration, I'm going to start with some crystal geyser water. I know you probably can't see what I'm doing, but I just added some water. And now I'm going to add some bromothymol blue. Okay. And so we got this nice blue color. This water is a little what? With a blue color. 7.6 or greater is blue. So this water is what? Acidic, basic, or neutral? Basic. Now, I'm going to add an acid. Except the acid I'm going to add is I'm going to add the Lewis acid of CO2. Remember CO2 from Friday? So I'm going to bubble this. Is it easy to see here? Okay. Over here. I don't know. Doesn't matter. What color change? Green. Oh my gosh. It's between blue and what? Yellow. Between blue and yellow. What happened? You've got both the conjugate acid and the base in equal quantities. That's why you're getting the green in between. And that's, now if I keep blowing, I should get what? but I have to go below 6. I'm not sure if CO2 is a strong enough acid to get there, but all right, well, I think I'm getting lighter, but I'm going to cheat. I'm going to add some hydrochloric acid because I think CO2 is such a weak acid, I'm going to fall over. So if I put some hydrochloric acid and I protonate these O's, it's going to change its shape so that the white light hitting this can only what? Yeah, make this form. And there we go. So indicators help us give us pH ranges. All right? So there you go. All right. I'm going to give you guys a break and then come back. We're going to start our rat, and I'll explain what that means. Yep.